Imagine sending a perfectly clear message. But by the time it reaches the receiver, it's weaker, distorted, delayed, and partially buried in noise. The information is still there, but it's much harder to recover. This gradual deterioration is called signal degradation, and it is one of the biggest challenges in every communication system. In the previous lesson, we learned that every communication system must deal with noise. However, noise is only one of many problems that affect transmitted signals. Even if no additional noise were present, the communication channel itself would still modify the signal as it travels from the transmitter to the receiver. As electromagnetic waves propagate through cables, free space, buildings, or the atmosphere, they gradually lose power. They may reflect from nearby objects, spread over large distances, arrive at different times, or become distorted by the transmission medium. The signal received is therefore never identical to the one that was originally transmitted. This raises an important engineering question. What exactly happens to a signal while it travels through a communication channel? Understanding these changes is essential for designing reliable RF systems. Signal degradation refers to any process that causes a transmitted signal to become weaker or different before it reaches the receiver. Several mechanisms contribute to signal degradation. Attenuation reduces signal power as energy is lost during propagation. Distortion changes the shape of the waveform. Delay causes different parts of the signal to arrive at different times. Multipath propagation creates multiple copies of the same signal that interfere with each other. In addition, noise and interference further reduce signal quality. Together, these effects make it increasingly difficult for the receiver to recover the original information accurately. Intuitively, imagine making a photocopy of a document. The first copy looks almost identical to the original. If you repeatedly copy the copies, each generation becomes slightly blurrier until the text is difficult to read. Signal degradation follows a similar process, where imperfections accumulate as the signal travels. Physically, consider a Wi-Fi signal moving through a house. The wave passes through walls, reflects from furniture, and is partially absorbed by building materials. Some reflected signals arrive slightly later than the direct signal, while electronic devices contribute additional interference. By the time the receiver detects the signal, it has become weaker and more distorted than when it left the transmitter. Mathematically, engineers model signal degradation as the combined effect of channel attenuation, time delay, multipath propagation, distortion, and additive noise. Communication systems must compensate for these impairments to recover the transmitted information reliably. Signal degradation affects every wireless communication technology. Cellular networks continuously adjust transmission parameters as users move through different environments. Wi-Fi systems change data rates depending on signal quality. Satellite communication compensates for atmospheric losses, while radar systems account for propagation effects when detecting distant objects. RF engineers use many techniques to reduce degradation. They design high-gain antennas, employ low-loss transmission lines, implement equalization algorithms, apply error correction coding, and use adaptive modulation to maintain reliable communication under changing channel conditions. At the system level, understanding signal degradation allows engineers to predict communication range, improve receiver performance, optimize network coverage, and increase the reliability of modern wireless systems. Signal degradation explains why communication engineering is far more than simply generating and receiving radio waves. Every successful communication system must continuously overcome the imperfections introduced by the transmission channel. A common misconception is that stronger transmitters completely solve communication problems. While additional power can compensate for some attenuation, it cannot eliminate distortion, multipath propagation, or other channel impairments. Intelligent system design is often more effective than simply increasing transmit power. Now that we understand how communication channels modify transmitted signals, we can explore one of the most important ideas in communication engineering. In the next lesson, we will answer a fundamental question: why is modulation needed? and discover why nearly every wireless system converts information onto a high-frequency carrier before transmission. In this lesson, we learned that signal degradation occurs when a transmitted signal becomes weaker or distorted as it travels through a communication channel. We also explored how attenuation, distortion, multipath propagation, delay, and noise work together to reduce signal quality and make information recovery more challenging. In the next lesson, we will explore why modulation is needed and discover why RF communication systems transmit information using high-frequency carrier waves. If you found this useful, like the video, subscribe, and follow for the next lesson.